Today's demo is on EMA's Constraint Manager for OrCAD. So we're going to bring up the Constraint Manager for OrCAD using the Constraints pull-down in OrCAD Capture. We're going to select Launch Constraint Manager for OrCAD. The Constraint Manager appears. Now you'll notice that it actually shows buses. So buses don't generally pass from OrCAD Capture into PCB Editor, but we can actually pass them using the Constraint Manager for OrCAD. And we don't really have to netlist to do this. All we need to do is say Update Board File. I'm going to select the board file. Let's select Constraints, Update, and click OK. Later on, when we go into PCB Editor, you'll notice that the buses will appear. So the first thing that we're going to do is create a constraint set, an electrical constraint set, using the C-Set Designer. So once it comes up, we can select any of the worksheets over here in the electrical domain and make sure that the electrical tab is selected here, and then hit Create New Electrical C-Set. We're just going to name it Rules. And then we're going to define the rules for several of the worksheets. We're first going to select the wiring worksheet, and we're going to select Min Daisy Chain for scheduling. We're going to set our maximum stub length at 200 mils and our maximum exposed length at 200 mils. The maximum exposed length will make sure that most of the net is routed on the internal layers. So since these nets come off of surface mount pads, they must run on surface layers for a small length. So we're going to constrain that length to 200 mils. Next, we're going to go into the via rules, and we're going to set it for a maximum number of 2 vias. We're going to set our impedance rule to 60 ohm and with a 2 ohm tolerance. Then we're going to set our min-max propagation delay, and we want our pin pairs to be set to longest shortest pin pair. Our minimum length is going to be 1000 mils and our maximum length 3000 mils. And that's it for our constraint set. Once we're finished doing that, we can simply click Exit. Now we're going to expand one of our buses and assign our new constraint set to that bus. So we're going to click and select Rule. We're going to assign rules to the bus itself. And you'll notice that each bit of the bus inherits that rule set. So the last thing that we're going to do for this constraint, for the constraints on this net, is we're going to go to the vias rule sheet. Actually, let's expand this back out again. And we're going to turn on the matched vias. So no matter how many vias the nets end up getting, 1 or 2, they have to be the same number on each bit of the bus. Now, before we go and pass these rules over to PCB Editor, we're going to do one more thing. We're going to create a relative propagation delay or match delay on our VD bus. So we're going to select the bits of the bus, right-click and say Create Match Group. And we're just going to call this VD_GRP for match group or for VD group. If we go all the way up to the top, we'll see our VD group. And now we're going to fill in our rules. So for our VD group, we want to use, again, longest shortest pin pair. We want our scope to be global, or G. The delta is going to be 0 mils, and our tolerance is going to be 25 mils. That means we have a plus or minus 25 mil window. Actually, we wanted 25 mils, not percent or nanoseconds. So let's change this. There we go, 25 mils. So now we're going to go ahead and update our board file again. So let's update the board file. Let's update constraints. Update. Click OK. Now let's go open that board file. Let's click Open, Constraints Update. And the first thing we're going to do is go and go to our display status and update the DRCs. And you'll notice quite a few DRCs pop up. Okay. We can go in and look at a few of them. So we have an electrical layer issue because we have this length here is longer than 200 mils. This net is running on the external layers. Okay. We also have a lot of we have some impedance rules. We also have some delay rules. It looks like on this bus here we have our match delay is apparently not matched closely enough. We can actually go into the Constraint Manager and look at some of these rule sets. Okay, so here's our bus. Let's see if we go to min-max propagation delay and click Analyze. Analyze this for us. Let's just make sure that all of our electrical rules are turned on. Oh yeah, so our via count is not turned on, our propagation delay. Okay, so let's just make sure things are turned on. There we go. So yeah, so now we can see that a lot of our delay rules have been violated already. So our minimum, our maximum we're okay with. That means we haven't placed our components too far apart to meet that delay. And now we can go to our relative propagation delay and we can look at our VD group. Let's expand our VD group, and we're going to analyze this, and we'll see that we haven't really met our delay. Okay, so and by using the longest shortest pin pair, it set the longest pin pair as the target. Okay, so we need to try and meet that. Now we could go in and edit our some of our net lengths and so forth to meet that delay. So this is the min-max propagation delay, and we can simply go in and add some of the here, let's not center that. So we can add this, and you'll notice the when our meter down in the lower right hand corner of our window turns green, we've now met our delay. Okay, so I'm not going to work on most of these. I might go ahead and slide this via over so that we don't have a problem anymore with our max exposed length. Okay, and oh, and that's another problem that we have, is we have too many vias. So most of these guys just have 2 vias, and this one has 3 vias. So we're actually violating our vias as well. So if we go to our via worksheet, yes, we can see that we've actually violated the worksheet. So, or we violated our via rules. Okay, so next, let's go back into our Constraint Manager. We can exit out of here. We can go ahead and save this board. And exit out of here. Oh, one thing I didn't really mention was that, let's actually go back there for just a moment and look in the Constraint Manager, and you'll notice that we actually have some of our nets are X nets. Okay, so that means that they are one signal path that traverses a discrete passive component. Now these, OrCAD does not usually recognize these, but we can actually back annotate them into OrCAD. Let's actually, instead of closing this, let's go ahead and just go with our start board. Now, so the first thing that we're going to do when we get back here is we're going to import the board data, because we want those XNets, but we also want the stack up, because next we're going to be creating some physical rule sets. So let's go and select our constraints update board, and we want to merge with existing constraints. So we've already put some constraints, so we want to merge with the existing constraints that are already in the board. Okay, so now next let's go to our physical domain, where we're going to set some, it brought in our default rules here, by the way, as you can notice. We're going to create some differential pairs, and we're going to create differential pair constraints. Okay. So the first thing, let's go down and select our, and here it brought in a bunch of XNets too. Okay, so we now have XNets in our design that we can constrain. So let's select these nets here are going to be our differential pairs, or some of our differential pairs. So let's select them, hit create differential pairs, and now we're going to set our filter. So we want asterisk underscore P for the filter, and oops, let's hit underscore. And then we want asterisk underscore N, okay, as our other filter. And then we would like to add DP underscore to the beginning, so as a prefix for the names of our differential pairs. So let's select assign pairs, and if these look good, we can go ahead and click save. They get added as differential pairs. Next, we're going to go down and select, we have 8 more signals that we want to create differential pairs with. So we'll do this real quickly. Underscore P, underscore N, DP underscore is our prefix, assign pairs, and click save. Now let's scroll up towards the top. We should be able to see our differential pairs. Okay, so here's all of our differential pairs right here. Now the first thing that we're going to do is we're going to create a physical constraint set for the differential pairs. So we're going to go back into our C-set designer. This time we're going to select nets by layer in our physical C-set. And we're going to select, which automatically selects the physical tab here. And then we're going to select create new physical C-set button. We're going to name this "90 O." Okay. And we're going to set the rules for it. So most of the layers we're going to set at 5 mil line width, but the top and bottom are actually going to be 8 mils. So our external layers are 8 mil, internal layers 5 mil. We're not going to set a maximum width. That means it will be unconstrained. Our neck width will be 4 mils on all layers. And again, we're not going to set the maximum length. Our primary gap is going to be 5 mils on the internal layers and 8 mils on the external layers. Our neck gap is going to be 4 mils on all layers. Our tolerance is going to be 0.5 mils plus and minus. So that's our tolerance for our primary gap, which means that our minimum spacing is our neck width minus the minus tolerance, which gives us 3.5 mils as our minimum line spacing. Okay. So that's our 90 ohm differential pair constraint. And by the way, you can actually look at this. Let's expand this so we can look at different layers. You can look at this by looking at the using the diff pair viewer. Okay, so right off, let's select our top layer, okay, which gives us 8 mil lines with 8 mil spacing, and you can see when it necks down, it goes to 4 mil with 4 mil line spacing, and you can actually see that there's like a 0.5 mil on either side. This right here, this line in the middle, is our minimum line spacing. Okay. Now if we select one of the internal layers, we can see that our min line width and spacing is different. Okay, so it's very easy to see the difference between the external layers and the internal layers. But in both cases, the neck width and neck spacing is the same. That doesn't change. Okay. So let's exit the CSET designer. And in our physical domain, let's go ahead and assign the 90 ohm constraint set to the differential pairs. And next we're going to go into our electrical domain and back into the CSET designer, and we're going to create a constraint set, an electrical constraint set for our differential pairs. So we're going to select one of the worksheets, so the differential pair worksheet in the left pane. Then we're going to select, which gives us the electrical tab here. Then we're going to select the create new electrical CSET here, and we're just going to call it DP. And let's fill in the constraint. So our gather control we're going to set to ignore, which means that it's not going to include the length between the pins and the point at which the nets gather at their ideal separation in the uncoupled length calculation. So we're going to, ignore. We're going to ignore that length, and we're going to set our max uncoupled length at 200 mils. Our static phase, so the difference in the length between the two members of a pair overall can't be more than 25 mils. Our dynamic phase, which matches the length difference at every bend, we're going to set at 0 mils but with a 25 mil tolerance. Okay. So let's go ahead and exit this. And we're going to go down and find our differential pairs again, and we're going to assign the differential pair constraints. So we can select all of them at once and then assign DP. Okay. And lastly, all we really have to do is update the board again. So let's update the board file, the same board file. And let's go back to our board. Let's open up our constraints update. And now if we go in and look at the constraints for our differential pairs, you'll see that they're all set, which means we should be able to just go ahead and route. So if we go into route, pick up a differential pair, you'll notice that it, let's get a vertical, there we go. Goes ahead and route, and you'll see that the line width and spacing is definitely different on the external layer than on the internal layer. And we can go ahead and route the differential pair. Okay. So, and that ends our demo for EMA's Constraint Manager for OrCAD.